So I'm going to try to convince you that Jacob-Lurie's non-abelian Poincaré duality isn't general enough. I think it's a common complaint about theorems by Jacob-Lurie. Yeah, so first I'll give you a sort of slightly different perspective on what Poincaré duality is. Normally Poincaré duality is like you have two chain complexes and they have the same homology. I'll talk about like here you have two spaces and they have the same homotopy groups, or the spaces are homotopy equivalent. So add like the pi, yeah. And that'll sort of lead into the definition of like factorization homology and the statement of Lurie and Salvatore's statement of non-abelian Poincaré duality, and then I'll explain why we might be interested in generalizations of it. Okay, so we're looking for a space level version of homology, and so the first part of the talk, the story, is roughly due to Sadik Hillel and Jacob-Lurie. Yeah, so I'm not taking like credit for this like. They didn't prove Poincaré duality originally, but like the story about how to think about Poincaré duality. Yeah. Okay, or at least I learned it from their papers. Okay, so definition. So so for a space X, let Z of X be the free abelian group on X, and so Spence had said we can only draw one space. So we want to topologize this space. So you can think of a point in this space, if this manifold is X, as a configuration of points labeled by integers. And I want to topologize this space in such a way that when points collide, you add their labels. So this point is walking in this direction, this point's walking in this direction, that configuration converges to, can I add correctly, 1, yeah. And also like this point labeled by 4 can split up into, 6 points, 5 of them labeled 1 and 1 of them labeled -1, and that's a continuous family in the space Z of X. So why am I saying that this is a good candidate for homology? Well, a variant of the Dole-Tom theorem says that the homotopy groups of the free abelian group on a space X are isomorphic to the homology of X. And I guess it'll be relevant later, a relative version of this. So if Y is a nice subspace of X, then so you can form Z of X is a group, and the group on Y, is a subgroup of that. So you can form the quotient, topologize it in a natural way. The homotopy groups of this space are just the relative homology groups, X, rel Y. Okay, so this is our space version of homology. What's our space version of cohomology? Well, we all know that Eilenberg-MacLane spaces represent cohomology, so it's a statement that pi 0 of maps from a space, I call it X. Is there? Oh, there's an eraser. Yeah. From X into a KZN is isomorphic to pi n of X. Sorry, is isomorphic to H upper n of X. And, slight generalization, pi I of this space is Hn minus I of X. So, like this space is going to be our candidate for space-level cohomology. So really, Poincaré duality for, well, so I'm going to assume all my manifolds today are parallelizable for convenience most of the time. So like we don't so Poincaré duality, like isn't the statement homology equals cohomology, it's a statement homology equals twisted compactly supported cohomology. But the, so I'm going to ignore the like twisted because I'm assuming everything's parallelizable, but I'm not going to ignore the compactly supported. So, if you want compactly supported cohomology, take the space of compactly supported maps. So like pick a base point in this space. Yeah. So we want to compare. Yeah. So like our goal is to build a map. So our goal is to build a map from the free abelian group on a manifold into the space of compactly supported maps from M into a KZN that induces a homotopy equivalence. And I'm going to call this map a scanning map. I'll call it S. And so what's, from the perspective of this Dole-Tom theorem, what is our favorite KZN? Well, if you take an n-disk rel and n-sphere, the homology of an n-disk rel and n-1 sphere is z in dimension n and 0 everywhere else. So by the Dole-Tom theorem, a model of a KZN we could take to be z of an n-disk mod z of the n-1 sphere. And now it looks more plausible that we'll actually be able to build such a map. So the way that this goes is, I guess we're going to define the adjoint of the map. So we're going to find like a So the way this works is yeah. So let's say we have little m in here, and probably getting too ambitious with colors here. Squiggle is the configuration in this space. How do we build a map like this? Well, so we have this point M, and we have this configuration. One over here. What do we do? Well, we pick a ball B around M in some continuous manner, maybe, picking a metric on the manifold and using the exponential map to pick some small ball. Maybe it's not that small in this picture. And what we do is, so there's a map from Zm to Zm mod M minus the ball. And then we use the fact that all manifolds are parallelizable today to identify, this is, I guess, sort of an excision statement, to identify, so like this is maybe naturally isomorphic to like Z of, maybe it's a closed ball mod, the boundary of the closed ball, and then we use the parallelization to identify this ball with the standard n-disk. And the proposition, which is maybe a folk theorem, is that S is a weak equivalence. And corollary, you take homotopy groups of this statement, you get Poincaré duality. So it's reasonable to say that the fact that the scanning map is a homotopy equivalence is a Poincaré duality type statement. Yeah. So now the natural question would be, okay, like Poincaré duality is true with, Z mod 3 coefficients. How do you, is there a space level version of that? And of course, you do the exact same thing. Is this going to work? No. No. Like, yeah, so it's, like, we just want to point in here. So a point in here could have 10 million particles.
Okay.
So it doesn't matter if they're 10.
It's always becomes equivalent. It doesn't matter what ball you pick.
It doesn't matter what ball you pick.
Okay.
Yeah.
You pick like a continuous family of balls for every point down.
Yeah. So you're going to need, like, if you want to pick a metric, say something like some radius less than the injectivity radius. But like in the configuration space case, there's like the second closest point argument, and you don't need to make it here. You don't really even need to make it. You could make it there in a different place, but yeah. Because, I mean, like, you could have one point. We could have one point in the configuration at our green dot labeled by, 10 trillion, or, I mean, even not labeled by anything, but then it could split up into 10 trillion points labeled by 1 and 10 trillion points labeled by -1. So you can't continuously pick some distance where you're not going to have, or you only have one point in this case. Okay. So in general, so like, in general, you can copy the exact same proof. So like, let A be an abelian topological monoid. Let A, capital A. Close enough. We're on a schedule, so yeah. Okay, and you get the same statement. You get that you can build some configuration space of particles in your manifold labeled by A, and the scanning map is a weak equivalence. So if A is a discrete abelian group, I could just write KZ or KG n if K A n here. But if this is a topological monoid, the correct thing to write is the n-fold delooping of A. So A is an abelian monoid. You apply a simplicial bar construction. You get out an abelian monoid. Apply it again, etc. And this map is a weak equivalence if pi 0 of A is a group. The monoid structure makes pi 0 of a monoid into a monoid, and if that's a group, then this map is a weak equivalence. Okay, so now what happens if A is not abelian? So what A is not abelian? Well, so we have a point labeled by little a point labeled by little b. What do you want this to converge to? Do you want this to converge to like A times B, or do you want that to be B times A? And you don't know. So this construction doesn't work when A is not abelian, except in dimension 1. So if the dimension of M is 1, so there's point C over here, and there's point A, there's point B, I want that to converge to A times B. And our manifold's parallelizable, so it's like multiply the one on the left first, and left makes sense. Yeah, and so you can form this construction, and the scanning map is still a weak homotopy equivalence even in dimension 1, or sorry, like even when A is not abelian if you're in dimension 1, so you know like what this thing means. And so you say like, oh, are we just doing this for fun? Well, this scanning map recovered Poincaré duality. The non-abelian dimension 1 case recovers a theorem. I've said of Good Willie. Someone said this was like known before Good Willie. I don't know. I'm going to following corollary. So this is a statement that the Hochschild homology of chains on the base loop space of a space is isomorphic to the homology of the free loop space. And so how do you recover the corollary? Well, so like the base loop space is you can have a monoid, strictly associative monoid model for it using Moore loops. So you look at like base loop space of X of S1. I'm saying this is homotopy equivalent to space of compactly supported maps from S1 to the de-looping of loops X. Now we take homology of this statement. So compactly supported maps out of S1. S1's compact, so we can forget compactly supported. This is the definition of free loop space. The de-looping of the looping, so I need like X connected. When X is connected, the classifying space of the loop space of X is just X. So this is obviously this. It's not so hard if you filter this space by the number of points to see that that the homology of this space is just the Hochschild homology of chains on the base loop space. So in dimension 1, we got out this like not completely stupid theorem that the chains, the Hochschild homology of the chains on the base loop space are the homology of the free loop space. Okay, so that's like maybe one reason why you might want a this non-abelian Poincaré duality phenomena. So this non-abelian Poincaré duality tells you this statement about Hochschild homology. So maybe there are interesting things in higher dimensions. But we still have this problem of like how do we define this thing? And the answer is, well, in my opinion, non-abelian Poincaré duality is a misleading name. I think it should be called slightly less abelian Poincaré duality. So we're not going to be able to define this space in higher dimensions when A is non-abelian because, like, what are you going to do about this? However, we're going to want a level of commutativity equal to the dimension of the manifold. And then, like, we will be able to make sense of this construction. So yeah, so like if the dimension of M is greater than 1, well, what are the ways in which points can collide in dimension n? Let's say equals n. Well, we have a Sn minus 1's worth of directions at which points could collide. So we want an algebraic structure where the space of 2-to-1 operations in our algebraic structure is homotopy equivalent to Sn minus 1, which I guess we've been calling, which is, or another way of thinking about it is like the configuration space of 2 points in Rn, 2 ordered points, which I guess we've been calling conf, maybe. And what do we want the space? Conf 2, yeah. And but like, what's going to happen when 3 points collide? Well, we want an algebraic structure such that the space of 3-to-1 operations is homotopy equivalent to conf3 of Rn. Here I knew another name for it. Here I don't know another name for this homotopy type. Because you might have 3 points moving around and colliding, and you want, yeah. So if you have like a fully commutative gadget, you can do this construction in any dimension. If you have, so like the name of this thing is going to be an EN algebra. And if you have an EN algebra, you can form this construction in dimension n, and then the scanning map will be a weak equivalence, and yeah, and I'll tell you why you might want that, but why you actually want even more than that. Okay, so yeah, so like what is an EN algebra? I mean, so there is a definition in terms of like compactifications of configuration spaces where the model of factorization homology is exactly this configuration space model. I'm going to use sort of a bigger, model just because the Fulton-McPherson operad is a little bit less friendly than little disks. But we'll pay the price of like needing some simplicial machinery. Okay. So definition. So let dkm be the space of embeddings of k n disks into your manifold M, and let dmx for a space x be, let's write it out first. So this is like the configuration space of ordered parametrized disks in your manifold M, and this is the configuration space of parametrized but unordered configurations of disks in your manifold M, but labeled in your space X. So a picture of a point here is we've got some disks, and each disk is labeled by a point in X. Okay. And the definition of an EN algebra, which is going to be the the algebraic structure where all of these which allows us to form this configuration space in higher dimensions, is the following. So definition, an EN algebra is a space A and a map from disks in the n disk labeled in A to A. Also, there's a unit map, but who cares? Satisfying, I don't know how to spell, a bunch of conditions. And what are the conditions? Well, I'll tell you examples, and that's better than telling you what the conditions are. But it's like you should think of it as sort of, they're just sort of associative conditions. Associative. They're like sort of analogs of like group action conditions. Okay. So yeah. So what are examples of EN algebras? So uconf. So unordered configurations in the n disk is an example. So what is a picture of element here? Well, maybe we'll name the structure map. I don't know what the name of the structure map is. C for like composition. Okay, so a point in here is a configuration of disks in a disk labeled by particles in a disk. And so how do we get from a picture like this to a picture of like points in a disk? Well, delete these circles. Another example is the space of compactly supported maps from an n disk to some space y. And yeah, so how do we find the map there? Well, so we have this compactly supported function. We have a bunch of disks labeled by compactly supported functions, and we need a compactly supported function from the entire disk, so just like extend by the base point. Yeah, so these like EN algebra structure maps you don't do very much. Otherwise, the diagrams won't commute. Another example, maybe where you do slightly more, how about like the integers? Or any strictly commutative monoid works. So like, this is 4. Yeah. Okay. Another well, so I guess like these rational function spaces are E2 algebras. These like bounded symmetric product spaces in the n-disk or EN algebras. Another non-trivial example, disjoint union of classified spaces of mapping class groups with one boundary component is an E2 algebra. I think nobody really knows like how to make that useful yet. But in some sense, like it was counterproductive because it maybe delayed Madsen-Weiss by like 5 years or something. Because it had a like there was an obstruction to like promoting that to a E-infinity algebra, which maybe made people not think that like its group completion could be an infinite loop space. Yeah. Insert ISIS. I'm not going to say, yeah. 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 Okay. So like what is, so the analog of this, so if you have such an EN algebra, then we build this analog, we're going to like change the notation for no reason. So we're going to, or not yet. Okay, so before I define this factorization homology construction for EN algebras, let me just say there's sort of two natural maps from disks in a manifold labeled by disks in a disk labeled by elements of A to disks in a manifold labeled by A. And probably I don't have enough room for this picture to be legible, but whatever. Okay. Okay. There'll be less disks than usual, maybe. A, B, C. Okay. So like there are two things you can do. Oh, no, now this is where the problem. One of them will go up here. Okay. So one thing you could do is you can just forget the outer disks like we do here. So we get a disk labeled by C. I've also been told it's hard to tell the genus from the disks in my talks. You can forget the outer disks. And here we didn't use that A was an EN algebra, but somehow we used that disks in a manifold is the right module over this operad, is the eraser map. Or we can, this is bad when I call this C. I don't know, whatever. Or we can compose and we get like, we'll replace this disk by the composition of A and B, also depends on like these disks, and replace what's inside this disk with the composition, this will be D. composition of D. And here it depends on this little disk. So this uses the EN algebra structure. So it's just saying there's a map from here to A, and you do that to all the labels of all the disks. And so you should think of this as like, hey, we want like A and B to be able to collide and be replaced by the composition of A and B. So like what you could do is you could try to take this space and mod out by the relation that like the image of these two maps are equal. But that's sort of a harsh thing, homotopy theoretically, so we're going to sort of mod out by it homotopy theoretically by taking some giant simplicial space construction. So what we're going to do is instead we're going to put in a path from here to here. So this is going to be our space of 0 simplices in this factorization homology space. And this will be a space of 1 simplices saying that there's a path from this point to that point, allowing these points to collide up to homotopy. And so like the 2 points collide and you multiply their labels, and it has something to do with the direction in which they collided. So how am I doing on time? 12 minutes. Okay, that's good. Yeah, so definition. So the factorization homology of M with coefficients in an EN algebra A is defined to be the geometric realization of a simplicial space. Now I say disks in a disk like 8 times. The space of 0 simplices is disks in your manifold labeled by, I had one extra disk, labeled by disks in A. The space of 1 simplices is disks in your manifold labeled by disks in a disk labeled by A. And there are these two maps that I talked about are the two face maps. The degeneracy maps are inserting like a unit disk everywhere. And the space of 3 simplices are disks in your manifold labeled by disks in a disk labeled by disks in a disk labeled by A, etc. I say disks in a disk one more time for the space of 3 simplices, etc. And this is sort of the homotopy theoretic way of allowing these 2 points to collide and produce the algebraic composition. Okay, so what are properties of this construction? Well, yeah, so this is some way of taking some construction that you do on Rn and globalizing it. So the factorization homology of uconf n disk is going to be homotopy equivalent to uconf of the manifold. Yeah, and here's where maybe I want the manifold to be parallelizable, or here's one of the places. The factorization homology of the space of compactly supported maps out of the n disk to some space y is the space of compactly supported maps out of m into y. And same thing like the factorization homology of Z, maybe it's not analogous, but the factorization homology of Z is homotopy equivalent to Z of M. What else do I want to say? The factorization homology of Siegel's rational function space is in Rn isn't the rational function space in over the curve, but it's this divisor space because there's some subtleties. But same obvious thing works for bounded symmetric powers. For this mapping class group example, we have no clue if there's an interpretation of its factorization homology. It would be neat if there was. Yeah, and then we get like a theorem. If pi 0 of A is a group, this is a theorem of, in some sense due to Bill Thurston and his work in foliations, Paolo Salvatore, and Jacob Lurie, that says if Yeah. Pi zero. You sort of need a theorem of Peter May to maybe promote it to the theorem of Jacob Larry. But yeah. Or to see that Thurston's theorem is full generality. Follows by like a theorem of Peter May. That then the scanning map from factorization homology of A to compactly supported maps from M to n-fold delooping of A, which I haven't told you what it is, is a weak equivalence. Okay, so this gives you some corollary, like the recognition principle of Peter May that says that if you have a EN algebra whose pi 0 is a group, then it's an n-fold loop space, because if you plug in an EN algebra is homotopy equivalent to the factorization homology over the n disk of A, which then is compactly supported maps from the n disk. This is like theorem May. I'm writing, I guess, the proof, and the theorem is like the final equality. Sorry. Compactly supported maps, which is homotopy equivalent to n-fold loops of BNA. So this says if you have an EN algebra and pi 0 of A is a group, then A is homotopy equivalent to n-fold loop space. Yeah. So you should sort of think of non-abelian Poincaré duality as the minimal generalization of Peter May's recognition principle and regular Poincaré duality. Yeah, but there's a lot of theorems that I think are cool that, so like factorization homology plays nice with configuration spaces. Deuce and McDuff and Graham-Siegel have a theorem that says that so like theorem McDuff-Siegel. There's separate papers, or combining two papers, not theorem McDuff-Siegel, that the scanning map from uconf M to the space of compactly supported maps from M into uconf disk. This space is the M sphere, by the way. And that's how they phrase it. But is I don't know how to spell, induces an iso on H star for, let's say, HI for I less than or equal to K. So here, if you just look at configurations of K points and you look at the component of degree K maps, then the scanning map, it's not the scanning map isn't a homotopy equivalence, but it's a homology equivalence in a range. And that's sort of the best you could hope for, because this space is a finite dimensional manifold, and this space has homology in arbitrarily high degrees, so you're not going to expect that it's a homotopy equivalence. Similarly, there's a similar theorem for, if you replace this by the natural numbers, this guy is disjoint union of symmetric products in a theorem of the actual Dole-Tom theorem plus theorem, 5 minutes? 4 minutes. Theorem of Steenrod. Oh, this is K over 2. The theorem of Steenrod is K. Says that the analogous thing is a homology equivalence in a range. Similarly, the analog of May, if you apply for not group like EN algebras, there's the statement that if you invert pi 0 of your EN algebra, if you take the homology of your EN algebra, that's a ring. You look at pi 0, that's a subset of the ring. If you invert that, you get the homology of this gadget. It's the group completion theorem due to McDuff and Siegel. All of those things seem like they're, like related to factorization homology. So all of those are about, are, I think, interesting theorems about not group-like EN algebras. And so you're wondering, like, is there some analog of non-abelian Poincaré duality for not group-like EN algebras? And the answer is yes. So this theorem, so let M be open and connected, then there exists what I'm calling a stabilization map. It's like a bringing stuff in from infinity map from factorization homology of M to factorization homology of M, such that when you invert this bringing stuff in from infinity map, you take the mapping telescope on this map, then the scanning map induces a homology equivalence from this factorization homology space to the same space of compactly supported maps from M into the n-fold d-looping of A. And so this theorem of McDuff and Siegel is really two theorems. It's a theorem of McDuff that when you invert bringing particles in from infinity, this space is homology equivalent to that space. And then a theorem of Siegel saying there's homological stability, so that actually the in the limit statement can be brought back down to actually say something about any finite level. So this theorem in particular gets the McDuff part of this theorem. This theorem, when you apply, when you say the manifolds Rn, you get the group completion theorem. Well, in the case of EN algebras, I guess, in the, when n equals 1 and it's just associative, you don't get all of the special cases of the group completion theorem. You get the Dold-Tom part of this theorem for symmetric powers. Yeah. But it would be nice to get the full thing, right? It would be nice to also have homological stability, so then you could actually know how destructive this bringing stuff in from infinity map was. And that's the topic of the second talk. So here we have scanning. Sandra will talk about homological stability.
Question to the speaker? How does this bring
Oh, yeah. I think I was just panicked and started saying a lot of stuff at the end. But I don't want people to miss their flight. So, a zero simplex in this space, is something like this. You pick sub point x and A, and you define t sub x takes this picture and sends it to, because the manifold is open, oops, the A shouldn't move. You can sort of attach a collar onto it, or at least make some room near infinity. Bring in a disk labeled by X.
A and B, and that's an accident.
That's an accident. Yeah. Yeah. Yeah, and so you can either just invert all maps. You can corresponding to generators of pi 0, or you could take all the generators of pi 0 if it's finitely generated, multiply them together, and invert the product of the generators. Yeah. So, yeah, and yeah. It's in the group completion theorem case, the stabilization map is just multiplication by an element of the monoid. So, you're inverting multiplication, but in the manifold case, it's, not multiplication, but it's this bringing stuff in from infinity map. And, at a higher level, if we had more disks, C, just put two circles around X to get the map on one simplices.
More questions? The twin model for this theorem is if you choose M to be Rn and A just to be configurations, right? And this is essentially amounting to homological stability for configuration.
Well, it's not. This is amounting to colim homology of U conf K Rn is isomorphic to homology of a component of loops n, Sn. But you don't get like a range. So for all you know, I mean, like in this case, stabilization maps are injective and homology equivalence is in a range. But for all you know, like the stabilization maps have huge kernels, and like maybe it's maybe we lost lots of information. No, this is why like Sanders' name isn't on this, because this came first. This is like a motivation for our like homological stability thing for factorization homology. But yeah, you don't need. And in fact, like this is true for any En algebra. This is true for any En algebra. But if your En algebra doesn't have homological stability, I mean, plug in the manifold as Rn, then like the group completion theorem doesn't say every single monoid has homological stability. But you can, the group completion theorem is still true.
Other question? All right, let's thank the speaker again.